Okay, so welcome everyone, and good morning again. We are continuing this week. Last week we did the sort of preliminary what do you call it? The sort of preliminary work that is required for signals and systems, just to remind people's, but to jog your memory on signal transformations, shifting things around in time, and what reversal of signals look like on the like. Then we spoke a little bit about system performance, um, causality, linearity, time invariance, and so on. And then we spoke about these special signals that we use a lot in engineering. The impulse, which has its own properties, very special properties, not a real signal, but we sort of can approximate it, its behavior by doing certain things. Then a step which you can actually create, a ramp which you can actually create, and the sinusoid. So today what we're going to do is to just do a quick review here now of something called the transform techniques, and we will tie that in as we sort of move forward now into the meat of the program going forward here. So today we're talking about the Laplace transform itself. So that should be a review for you. A guest link for this class. Okay, give me a sec. Yes, there's a guest link. I could put it up in the chat right now if you give me half a second for people who may not be able to attend. Hold on. I didn't know that there were still people who were having difficulties. Right, so just a second. Okay, so I just put the link for the guest link in the forum. So anybody who is interested, you could copy it and send it to your colleagues as a need maybe. Okay, so transform techniques. This is actually quite common in mathematics and in engineering and in sciences as a whole. And the idea behind a transform technique is that originally you have some problem that you have to solve or model, and the particular domain, like the domain that we are in, which is the largely the time domain, that yes, you can solve it, but it's very convoluted. So the transform techniques now allow us to move the problem to sort of redefine the problem in another domain. And in that domain, we can do the manipulations and we can even solve the problem in that domain. And then having solved it, we have to now come back into the time domain, right? So we go to another place, it's like science fiction. You go to another universe where things work a little bit different. So gravity is up instead of down and all that kind of thing. But somehow they transform, if it's clearly, carefully done, allows us to do some manipulations that are a lot easier across there. And then once you are satisfied with what was done, then you can now come back into our own realm. As it turns out in electrical engineering, a lot of the time we can do our work in the domain itself. So we tend to stick around there, and people sometimes, students included, tend to forget that, wait a minute, that we are here and we're doing all our modelings in the transform domain, wherever that is, whatever that looks like. But at some point in time, you have to come back to reality. You must go back to the time domain at some point in time at the end, and hopefully at that and then you continue in the real world and you get your components and the like and so on. All right. In our case, we are going to focus on three transforms for the course. The first is the Laplace transform, so it's not really that we're focusing here on an entire course, a one credit course in that, which was ECNG 1016. And today we're going to just review some of the material for that. And as I have here down in the little note that the material for that course is the Laplace transform material that you learned is useful or essential for controls, communications, and energy systems. So if you're still rusty on it, and even after what we do in our own review here, it's something that you should go back and at least until you finish the program, keep the skill set for doing the Laplace transform fairly close at hand. We are going to also introduce something called the Fourier transform, which is a version of the Laplace transform. So it's very similar. The properties are very, very similar to the Laplace transform. And then we're going to look at a discrete time transform, which is called the Z transform. I have a little note here. Because of the similarities, not really three sets of new work you're going to do. You did one already. The Fourier transform is very close to the one that you did already, which is the Laplace. And the Z transform is really the only totally new one that you would not have met anywhere else before. So it's like 1.5 sets of new work. And just to put it in context, every time, for instance, as a matter of course, every time you take a photograph on your phone, the phone does a particular type of transform called a discrete cosine transform, or DCT. So it converts the image that the sensor on the phone camera picks up, or in fact any digital camera. They all do the same thing, and this is how that type of photograph code that you know as a JPEG. It is a transform that is done on the picture. So it gets the raw information, all of the spots, the pixels of the camera, and it does this special transform called a discrete cosine transform and converts it into, after a little bit of manipulation, it converts it into a JPEG. If that wasn't possible, you would need too much storage for every picture that you take on the phone. The JPEG is substantially smaller in terms of file size than the original picture that came off of the camera once it gathered the information. So this is just one of them, and there are other transforms that they use in oil industry and in communications and the like. And the good thing about it is now, because of computer techniques, that they're able to actually implement these things in an automated fashion. All right, so they're all over the place, and you'll meet them from time to time as you go forward. If you do image processing in year 3, Dr. Puransing's course, if any of you all ever do it, you'll come across that cosine transform and how it works quite a bit. Right, so the Laplace transform, of course, the definition of it was that the Laplace transform of a signal xt, right? The Laplace transform is that you took xt, you multiplied it by this exponent, which is e to the minus st, and s is a complex variable, so it has a real and an imaginary part, and then you integrated it over all time from minus infinity to infinity. And well, officially in the definition, this is known as a two-sided Laplace transform because it runs from time going from minus infinity to infinity. Why this works is a very long, difficult sort of process to understand in something called transform theory. But as we mentioned before, somebody likes the name Heaviside in the chat, and they keep bringing it up. But this electrical engineer, Oliver Heaviside, actually was the one that looked at the mathematics, and without delving too deeply into why the mathematics worked, he figured out that, wait a minute, this is great for my work. He was doing some engineering work, and it allowed him to solve these differential equations by applying the technique. And it's sometime after that this guy Laplace, Pierre Laplace, actually realized what the mathematics look like. You see, the thing about it, and this is what I have to tell engineers sometimes, these sorts of expressions here. And you learn it from your ad maths and your A-level calculus and so on, we tend to look at this thing and we just take it as is, that the definition is an integral of something multiplied by something, and we work out the math, and we do it well. But in truth and in fact, as the mathematician's approach to this has to first off define this function, and this function must be continuous. You remember us talking about that? It must be continuous. It must be integrable. In other words, if you integrate it, normally it must have some sort of limits. You remember, integrals are limits. Then e to the minus st, the same sort of thing. And then this whole function must be defined, and you have to prove that the integral converges and all those kind of things. You would have come across those terms in the mathematics already. But as a formal definition, a mathematician wouldn't just integrate this thing. You would have to prove that that integral first off exists, and only then we can evaluate it. We take the heavy side approach, which is that, yeah, it exists, and we go ahead and do it. But the warning is that not everything, not every time you will get an xt that you can, in fact, find a Laplace transform for. So you have to be a little bit careful with that, and it's just a caution. All right? Especially if you're going to do, if any of you all decide to stick into academics and you decide to do things like, not so much a master's, but if you eventually want to do things like a doctorate, the mathematics involved in the transforms and so on, that you have to sometimes go ahead and take the mathematician approach and understand what's happening first before you come out and say it. All right? So we're lucky. Of course, because we limit ourselves to causal signals, and remember we discussed that last time, and causal signals are those signals that only occur when we start to look at them. In other words, only when we turn them on, and we assume that they don't exist until we actually start to observe them. Then the lower limit of the Laplace transform, instead of going from minus infinity, we started at 0. And again, we do a little bit of a change for us. We use a lower limit, which is just before 0, because we say that causal signals, these things, change at, oops, getting trouble here, t equal to 0. So our signals change at t equal to 0, and you cannot do an integral if the lower limit, or if any of the limits, at the time of the limit, the signal xt is changing. So mathematically, I can't integrate xt at t equal to 0, because xt may be changing, like a unit step function, for instance, may be changing at t equal to 0. So just to make the mathematics a little bit correct, we back off just before 0, and we integrate so that the signal, we are integrating from a little a microsecond before 0, and we integrate across 0. So that it, for us, we just substitute 0, and it makes actually absolutely no difference in the arithmetic of it. But it is more mathematically correct for us because of the fact that we have to deal with causal signals, and we defined our causal signals as changing. In other words, they were continuous right across. They started to change at t0. Does it make it less causal? Less in our context, because 0 for this thing, this 0, you would have come across. I mean, I'm sure in your physics and sciences, you came across this thing infinitesimal, F-I-N-I-T-E-S-S-I-M-A-L, infinitesimal. Hopefully I got that correct. So 0 minus is infinitesimally close to 0. In other words, it is immeasurably close to 0, but it is not. So the thing is if you want to be correct, Sadie, it's slightly less causal, slightly non-causal, but for all intents and purposes, we treat it as such, okay? It's just to make the math correct. And when you evaluate the Laplace transform, you use t equal to 0, okay? Yeah? So this really is just not to tick off the mathematicians who say that they can't integrate at the same time a limit is changing. You can't integrate if a function or not. If a function is changing the same time as one of the limits of integration, you can't do that. That's mathematically incorrect. Yeah. Just for correctness purposes, and every so often you have to do that. And then, of course, you're supposed to know some of these transforms. Normally in the exams and so on, we give you, but it saves some time if you know a few of them. So the delta t, the Laplace transform of an impulse is 1. The Laplace transform of the unit step is 1 over s. The ramp, an exponent e to the minus at is 1 over s plus a. Cosine is s over s squared plus omega squared. Sine is omega over s squared plus omega squared as well. And then there are two other ones that come into play is a e to the at cosine omega and e to the at or e to the minus at sine omega as well. All right, decaying sinusoids. All right, you know that the e to the minus at is something that looks I'm having a little issue here. Right, so e to the at would look like that. Right, the cosine, of course, is the regular sinusoid, but a e to the minus at by that would be a sinusoid that does something like that, right? Right, actually there's more sine than cosine, but yeah. So something that behaves a bit like that. Right, so all of those things, dying sinusoids, decaying sinusoids, and exponents, those occur in what we do a lot. So at least it saves time if you know some of these things by heart. And I'm sure you do. Right, so again, as far as we are concerned, there are some important properties for us, and this is where the thing helps us out. We know that in electrical engineering, circuit theory, and in describing a lot of things, that we land up with differential equations. So that the main benefit for us of the Laplace transform is that it can take the differential equation and convert it into something that is pure algebra. And if you remember, if xt transformed has a transform that is xs, then the dxt dt had a transform that was s xs and minus this initial condition here, x at 0 minus. In other words, did x have some value just at the time when it was changing? Was it did it have an initial condition? And then the second derivative, second order derivative, which is d2x dt squared, was sx squared minus x sx, the initial condition, and dx dt evaluated at t equal to 0 minus or 0 minus. And of course, you know, to do this, we just let we let t equal to 0 when we evaluate it, but we know mathematically it really is a little bit before the 0 mark. Yeah, and you remember all of this. You did this and you spent some time doing all of this, and it's simple revision. Sometimes you forget it and you have to go back, but do so before too long. All right, and of course, the first order differential equation, or the pure first order differential equation, complete, would involve a first order derivative of both the output and the input. Okay. So both the first order derivative of the input and the output. And if you apply the Laplace transform all the way across, and you could check the equation here just to make sure that is correct, always do that when you have notes and slides to make sure. Sometimes you type in equations and signs get changed around the place. So you apply the transform, you group the y-s's and the x-s's together. If you're dealing with a causal signal, then remember that the input is 0 before t equal to 0. So you could set that to x0 prime, x0 minus to 0. You substitute above, and then you simplify. And if that is the case, then you get an overall expression after you have applied it now. So you're now in the S domain, as we call it, or the Laplace domain, right? You've gone across to a different place now, S domain. And in the S domain now, the output response, Ys, is given by this two-part expression. One part that has to do with the initial condition, and we call that part the initial condition response. And then the other part that depends on xs alone, which we call the input response. And of course, there's a little warning here that xs, in order for this to work, of course, you must be able to find the Laplace transform of xs. Certain things like last week when we discussed piecewise continuous signals, if you have a set of piecewise sinusoids or cosinusoids or exponents, sometimes it's very, very difficult to calculate xs in a situation like that. All right, so these things work within reason. And remember, back to what I was saying, what we're trying to do is model a system. And we model the system by trying to get it into a stage where we have some predictability and we can analyze it. Usually, for our purposes, of course, xs will be the impulse, right, the step, or the sign, right? Sign meaning sine or cosine. All three of them have Laplace transform. So if xs is known in these cases, and we will take it that even if the system has some discontinuities and so on, that we will, for the time where the input is continuous, that the transform exists, and therefore we could apply it and use it. Fair enough? Yeah, makes sense? Yeah, great, thanks. So let me go forward here. All right, so we have it, and then in this particular case now, if xs, as we said, is an impulse, sorry, if xt, sorry, is an impulse, xs is 1. The Laplace transform of an impulse function is 1. So that if you do that and then you ignore the initial conditions, so ignore this, right? Then at what? Then if xs is an impulse, then what we get is a particular expression here, left, which is the output over the input transform. And this particular expression or equation, sorry, we define in engineering as something called a transfer function. So whenever anybody tells you that so-and-so has a transfer function of, and they define it, the transfer function, they immediately telling you, one, is a Laplace transform you're dealing with, and two, that the input to come up with that Laplace transform was an impulse. Right? So in the formal definition, the transfer function is the Laplace transform of the input, the impulse response of a system. All right, and from that now, we can move in all sorts of ways, and we will see how we manipulate that a little bit later and the usefulness of that. We could then take that and we could expand it and go to a second order system. A second order system has a D2 d2y and a d2y dt squared and a d2x dt squared in here. And again, if we assume a certain amount of causality, then we could ignore x0 minus and x prime at 0 and go through the process, make the substitution, check the math and the signs. Remember the minus signs inside of here. Then you group all the y-s's on one side and all the x-s's on the other. And if you did that and you were careful, then you get the response for a second order system. And again, it has two parts. The output response is composed of the initial condition response and the input response. Now, this initial condition response may well be, for instance, if you were dealing with things, if you were dealing with like a series LRC circuit and the capacitor was not discharged, so you did some experiment on the circuit, you switched it off, and then you came back a while later and then you put it back on again. If you're doing it and you did not discharge the capacitor, so the capacitor may have a value, a voltage still stored in it. At that point in time, it means that y0 minus has a value. Okay, so that is why you call it the initial condition response. The safe thing, of course, if you're doing a model like that, is that you make sure and you very clearly state up front that assuming the capacitors and all energy storage elements in there were set to 0 at the time when you did the modeling or the testing. And then, of course, you have the input response, right? And then if xt is delta t, right, then this bit here is what we now call the transfer function of the second order system. Right, so ignoring the initial conditions here, you have the transfer function of the second order system. And of course, you could keep going and you could have third order and fourth order systems. But what we do, and we will see that when we a little bit later on when we're analyzing systems, is that in engineering, for us, all you really need is first and second order. That's now first and second order, because out of these I could break it down into any combination, any higher order one. I could break it down into any combination of a first and a second. So for instance, and I'm sure you met the term cascade in electronics already. Cascade, right? Cascade just means one unit following another unit. So for instance, a third order system, I can make up by having a first order followed by a second order. A fourth order, I can have a second followed by another second. Fifth, 1, 2, and 2. So you see, by that I could take any system and break it up into a combination of first and second order systems. And we do that a lot, and you're going to meet that as well when you do your control systems later on. Okay, so we really only need to know, in theory, up to the point what a first and a second order system transfer function looks like. All right, but of course we need to manipulate everything else going forward. Right, and in general, any order transfer function will be a polynomial. The numerator polynomial has some maximum coefficient n. The denominator has some maximum coefficient m. And for it to be a legitimate or a rational polynomial, m has to be bigger than n. All right. So in other words, if it was a third order polynomial, I would have s squared plus something on top, and s cubed This stylus is giving me some issues. And S cubed below, yeah, for it to be a rational third order polynomial. M specifies the order of the system, right? So you always look at the denominator, and whatever the order of the denominator determines the order of the system itself. Okay. So any questions on that sort of brief general review of what we're doing and why we are doing it? Everybody all right? Yeah? All right. And of course, you have to go and look at your own stuff. So let's move on to the second. So stop sharing this one. And we start here now. Right, so something called poles and zeros. So you have the transfer function, and anytime you're given a polynomial, right? Now we are specifically dealing with a polynomial in S, but any rational polynomial, rational meaning that m greater than n, it is possible to factorize a polynomial of both the denominator and the numerator. All right, so you can take it, and if you start off with a 4s to the fifth plus 5 s4 to etc., you could factorize it now. And if you factorize it, you can get it in this form with a series of factors on the numerator and on the denominator. And we give those particular factors, which are in fact the roots of the equation, of each of the polynomials above, we give them particular names. So in the case of the numerator, the roots of these numerators, every time you set s equal to any one of these values, so if I set s equal to beta 2, it means that s equal to beta 2 would make this particular thing equal to 0. So in other words, setting s to any of the values of any of the roots of the numerator, because it makes the numerator 0, we call those particular roots zeros. Yeah, really original. These now, on the other side, anytime I set s equal to any one of those alphas, by doing that, I am putting a 0 in the denominator, and it is making gs go to infinity. In other words, if you were to watch a graph of gs, at the point of s equal to any of the alphas here, gs, whatever is going to do, is going to try to go to infinity for each of those points. So at alpha 1, alpha 2, etc., it is going to try to go to infinity. This sharp rise is like a pole, like an electric pole. So they call it a pole. Yeah? So the roots of the numerator make gs go to 0. So let us clear all of this mess here. Any one of the betas, gs will be doing this. It will be going to 0. Right? So at beta 1, beta 2, whatever it is. So in other words, in terms of the transfer function, when s approaches these values, the transfer function, and remember what the transfer function is a model, right? A mathematical model of some system that we're working on. So anytime as s approaches one of these values, the system goes to 0. In other words, it shuts down. Okay, that is not too bad. Anytime s goes to, yes, poles are like a heart rate monitor. Again, I don't understand. What's that? Meaning?
So you hear me? Hello?
Yes, I am.
Okay, so like when you're seeing your pulse, like you would
Mm-hmm.
see it would have like a horizontal line and then it would have a sharp upward and then it a drop back.
Right.
I'm trying
Uh-huh.
to use that to refer back to to the poles and the zeros, right? So that's what I was trying to ask. Is it
Okay.
that those jumps within
Mm-hmm.
the poles and zeros? Would they consider
And
those?
no, no,
No.
no. Why? Because remember what we're dealing with. The heart rate, that heart rate thing that you're dealing with would be the kind of thing you're looking at the heart rate. So you're doing something like this. And I guess you talking about these bits here, right?
Yes, yeah.
Right. Okay. You have to remember one thing. This is time,
Okay, okay, understood.
right? That is the time domain. We're not there. We are in the S domain. So the
Right.
behavior is a little bit different.
Okay,
Okay? All right. But it's a good point, but not this is actually just a um what do you call it, a representation of what it is, but it doesn't quite mean the same thing. All
okay,
right?
no problem. Yeah,
But good question, and it's good
yeah.
to try. What I like to and for everyone, try to find an example or an analogy where what we're talking about could apply, and try to and clarify it. It may or may not apply. This raises a good point. So Akim's question is a good reminder for us. When we are in the S domain, we are not in time. We are in a different place. Okay, so what I'm talking about has nothing to do with how a signal or a waveform will look in time. We're no longer there. We're somewhere else. All right. And somebody was saying, or Sadie, that a third order system, but they are broken down into first S and not S cubed. Okay, you could clarify that for me, Sadie? The first part of your question, the third order system, but they are broken into first order, hence S and not S cubed, I think you mean. Um, what's that? Okay, let me just backtrack a little bit. All right. So what I was saying is that okay, so we have a system here, right? Just let me get a pen, right? And the thing about it is that this blackboard is, see, we had S cubed plus 2S squared plus 4S plus 5 over um over something like with S4 plus 5S cubed plus something, something, something. All right? Zoom this back up a little bit. Okay, so if this was a fourth order system, what we would try to do is this bit here, all right? We would typically try to break this up into something S squared plus multiplied by S squared plus something. And even this we could break up into S plus and go on, etc. Right? But we don't. What we try to do in engineering, for instance, is that we will try not to stick with the S4 part. We'll break it up so S4 could be an S squared multiplied by an S squared or cascaded with an S squared. All right? S cubed will be an S and an S squared example. I don't know if that clarifies what you were asking.
Good morning, sir.
Yeah.
Right. So you see how you have B and S to the end that is based on the the order of the system,
Right.
right? All right. On your next slide, you had S
Mhm.
minus beta one, beta two. The beta represents the order of the system.
No. The beta represents the roots of the system. So I could, you remember, look at this. Once we have the system, it is possible to factorize the polynomials of the numerator and the denominator. When you factorize, you remember the factors of an expression. Every time I tell you that, this is from your algebra or your calculus. Whenever you factor an expression, the factors that you get are in fact the roots of the expression on top here. So again, if I give you s squared plus 2s plus 1, right? If I give you that and I tell you to factorize that, and you tell me s plus 1 into s plus 1, it means that the s equal to minus 1 is a root. Sorry, s equal to, if I go here, this will be s plus 1 into s plus 1. So in other words, if I put s equal to minus 1 inside of here, this expression is equal to 0, is a root. Yeah? You remember that? So that when I factorize the expressions, all of the betas here and the alphas are the roots of that, whatever the polynomial for g of s was. So in other words, every time I put s equal to any of those values, in the case of the betas, any of the beta values make gs 0, and any of the alpha values tries to make gs infinity. They're just roots. Yeah? And good. So because the beta values tends to make gs 0, we give it a particular name. So we call the roots of the numerator polynomial the zeros of the expression. And I'll graph it out in a little while for you. Because whatever gs is doing, as it approaches the beta values, gs will shut down. Then it goes on again and it will shut down at each of the beta values. This is not too much of a problem. The real issue is this one. When when the value of s approaches any alpha, then gs wants to go to infinity. Now think about it. If you have an electronic system and it's operating like an amplifier, right? So you have an audio amplifier. And somewhere inside of here, certain signals or inputs are going to is going to be for whatever that amplifier is, the alphas for the amplifier. That's something that you do to the amplifier, some kind of input you're putting into the amplifier, somehow is going to cause it to assume one of those alpha values. In other words, the amplifier is going to try to go to infinity now. What is that? That means your volume all of a sudden for that particular value is going to hit the absolute maximum that it can hit. You don't want that. So the zeros tend to shut down the system, which at least is not going to destroy things, but it's certainly, you don't want that either. If you're driving a car and the system somewhere around the place, whatever is the behavior of the system, assumes a value of beta 1 or beta 2. And I know I'm talking a little, it's a little arbitrary here, but we'll see as we go along. The system will shut down, the car will shut down, the car be driving down the road and the car shut down. Same way, you're going down the road and some input, some combination of inputs causes the system to assume the value of one of the alphas for the system. Then the car is going to want to accelerate up to the maximum. You don't want that either. Right, so that's why it's important to know when you have the model. Remember, we've gone from time to this other domain, and in there now we're able to see these values for the system that is going to cause it to behave very strangely, in other words. And always remember how we got this. You remember this we got from time was a differential equation. So in our domain, our real world domain, we took something, it was an amplifier, it was a car or whatever it is, and we had a long set of equations that describe the car. We can't play around with those equations because they're hard to solve. So what we've done is that we take that set of equations and we go into another universe. And that other universe now converts those equations to an expression that we're looking like what we have here. And from this expression, we can immediately see that certain things are strange about the expression. That certain values make the numerator go to 0. In other words, this particular model, which comes from our differential equation, the model says that that system will shut down. And then if the model gets certain values in the denominator, which are the alpha values that we have up there, it causes the system to misbehave and want to basically go to infinity, could explode, to destroy. Right? You couldn't tell that from the differential equation, but we can tell it now. So our challenge as engineers and so on is that when you make the model, that you choose values of the alphas and the betas that will not occur in real life, or you make sure that if they are occurring, that you have the protection to deal with it. All right, and it's kind of going back to like when you were dealing with digital logic. You remember, if you're dealing with digital logic, there's a zone where neither a 0 or a 1 is recognized. So you have to make sure that you don't get values of signals coming into that zone. Or like when you did your Kano maps, you remember there were some values or truth tables, Kano maps and truth tables. There were some values that if they occurred in the truth table, the system you would have an unpredictable behavior. So you had to actually put in a value inside of there. Okay, it's the same sort of process here. So by doing the model, we've started in time. The Laplace transform converts us or carries us across into another world. And in this world now, we could do is kind of giving us an X-ray of what the system is like, and it's telling us there are certain behaviors of the system that will happen if it assumes if it assumes values. Yeah? Make sense? And K is just a gain, it's a number. So K is the amplification of the system. It could be anything from negative to positive. All right? So we go across here. So for instance, let's say this was a transfer function. And again, remember this came from a differential equation in time. Right? Which is some real world thing. So this came from a differential equation that described how a motor and a gearbox might be working, just for argument's sake. Right? We can't work with the differential equation, but we can't take the differential equation and we come into this Laplace domain, and we now have a simple algebraic equation. And if I were to just get the roots of the equation, you know how to find roots, you could do it all how, you could do it by inspection. So you could look at this and inspect it. So the first part, finding the roots here, is 3s plus 12 equal to 0. So you could solve for the values for s. S squared plus 2s plus 5 equal to 0. So what are the roots of the numerator and the denominator? And always remember that the roots could be real or they could be complex. Right? No hassle with that. You can always find out that. So what this is telling us is that this has a 0 at s equal to minus 4, and it has a couple of poles at s equal to minus 1 plus or minus 2j or j2. What we do again is that we take that and we can draw it on a diagram. Right? This diagram is referred to as a pole 0 plot. And notice where we are. We are in this place called the S-plane. Okay, like a higher metaphysical plane. We're in the S-plane now. And we draw where these roots are in this pole 0 plot. The x-axis is the real part, the y-axis is the imaginary part. We represent poles by an x with a circle. We represent zeros by a dot with a circle. So if you look at this thing, the origin is, this is the origin here, right? So this is the point naught naught, okay? So for that particular transfer function that we had before, you go across here and you see that I have two poles, one at minus 2, minus 1 plus 2j and minus 1 minus 2j. And then I have a 0 at minus, I can't read the diagram, I drew it over at s equal to minus 4. And the system, of course, has a gain of 3, an amplification of 3, right? This tells us certain things. So for instance, GS, if you were to plot, if you were to take, go back here, if you were to plot values now, so you let S, I mean, let's say graph it out. So you let S equal to a number of values and you start going through here now. G will have some sort of graphical behavior, right? If you look at it here, let me just get a different color here. G will do something, right? But at the point when it gets to, this point, it's going to go to 0. And if it approaches here, it's going to try to go very large. Same thing here. It could be doing something. If it approaches here, it's going to go to minus infinity. And you want to avoid that. So what, as a designer, what somebody will tell you is that what I'm going to do is, for argument's sake, whatever the system is, I'm going to only make it, let's say, operate right within this zone all the time. We're going to see that the position of the poles and the zeros determines something called the stability of the system. And it's very fairly easy to understand why, and we'll see it a little bit later on. Okay, so let me, at least for today, let me stop at this point. Here's another one, and you could try this. You have a hint that there are two poles at s equal to minus 1 and minus 2. So find all the zeros on the poles for this one and plot it on a pole zero diagram. You have it on the next slide, but try to do it and confirm what I have. All right? So let me take some questions here before I end off today's class, and we'll continue this tomorrow afternoon as well. So questions? What I need you to keep in mind is that this is a model, right? What we're doing here is that we're modeling, we exist in the time domain. The time domain description for the differential equation is very complicated. So what we do is that we decided we will go into the Laplace domain here, right? And we can manipulate this. So this, right, this here is the representation of the differential equation. And we can now manipulate that differential equation, and we see when we get there, when you get back to the inverse transform and so on, how again the complete relationship between the time and the S domain. But here now we can, in the S domain, we can look at certain behaviors that we can't very easily see once we are in the time domain. And if things, the idea behind signals and systems and some of the other courses is that if things look well and stable and what shall I say, controllable in the S domain, then it should be so when you go back into real time, which you have to go back to at some point. Yeah? All right? So that's all right. Any last minute questions? Think about it again, and tomorrow when we meet again, if there are any other, if there are things that you need clarified again, we will go through it, because that's what these classes are about, well, as we doing the transform review. All right? Okay, so I will stop the recording now. and